k equals 0 to t minus 1 of pi of c. All right? Because if I sum a constant, I just get the expected time times the constant. So anyway, exercise, this is equal to the expectation, again x, summation k equals 0 to t minus 1 of c of xk with a tilde. So, theorem. All right. Did it just in time. So, yeah. So really, basically all of this is just repeating the proof of that F-norm ergodic theorem. The use of this coupling here and all of that. But the difference is that I'm taking V, especially initialized here, to be able to argue. I'm not proving it here, but you could prove it, believe it or not, that this is exactly equal to that. The same argument. Yeah.
So if you didn't look at the discounted cost, then we don't have to go through the coupling, do we?
Say it again?
If we went through, instead of looking at the total cost, if
Yeah.
we looked at the discounted cost,
Right.
do we have to go through this way of the proof where we look at the coupling?
Oh yeah. Yeah. So yeah, for discounted cost, no, because for discounted cost,
We can.
I'll sneak that in here. So it's the same thing, right? I have Vn plus 1 equals, I put in a beta times PVn plus C. All right. Now, but what I want to convince you of is this is still useful. I would still want to use these arguments. Because, well, basically what happens is that I go through these same arguments and I would get a beta to the k here, right? And I would get my decomposition that you all look to get, that you all proved. I'd get the term here with the beta to the k, that would be the h tilde. I wish we had time. But if I went through every one of these steps, and everywhere you see a c of xk, put in a beta to the k, c of yk, put in a beta to the k. I go through all these things, and I can no longer apply Kack's theorem, but I've got this thing with it's a finite sum, and that's my h tilde. That's another derivation of that h tilde. And then I've got this this ugly thing here. Wait a second. Yeah, this is just a constant, and that's giving me my k beta, I believe, because this doesn't depend on x. But why isn't it blowing? Oh yeah, no, and then I've got. Oh, I'm sorry, I'm not taking differences. I'm not taking differences. It would be different, excuse me. This difference would be going to h tilde. Sorry. Yeah. Right, okay, no, can I start again? So, as you pointed out, the fact that if I do this with discounted cost, because of this strict contraction, as long as V0 is bounded, for example, Vn will go to the discounted cost, right? But I would still be interested in looking at the relative costs, because I would get a decomposition. I would get that the difference would be something, two terms that are bounded, which would be my H tildes. Yeah. Anyway, it's still valuable. That's what I'm trying to say. You still get insight from the coupling. We'll have to come back to this. I might have made a mess of that. So, any other questions about this? And by the way, the other, I mean, that MM1Q example is meant to point out why I don't like discounted cost. I mean, the discounted value function was bounded for finite value for any beta, any load. The load could be 1. The process could deterministically go to infinity, and yet the discounted value function was finite valued. So it's really, for a control person, it's not very satisfying. Somebody tells you I've optimized the discounted cost, and I look at it, it's an unstable solution. That's, I mean, only economists can get away with that.
We do.
What's that?
In practice, we do tend to use it, right?
I think it's mainly in operations research they push for that. I think control engineers typically do not. Yeah. I think the biggest reason for sticking and discounting is to compute things faster. Because if I put in a beta equals a half, this will converge like mad. And the convergence of this, the convergence rate of this is going to depend on the eigenvalues of P and stuff. It's going to, so it could be slow. But I called it the lazy approach because it's often the first thing to be done. Why? Because it's such a trivial thing to code. Look at that one line of code. But it's probably the slowest algorithm on earth. I mean, it's just it's probably the least efficient approach.
We need to know P and stuff, right? I mean, in a lot of practical problems that you might not even know.
We don't know P, and so that's why I'm rushing too to get to part 3 of the course. So we're gonna learn about how to approximate solutions to this equation when we don't know P. That'll be in the spring break. That's going to slow us down. But by the end of March, you will be able to code algorithms to approximate this. All right. Hopefully sooner. What do you do? So next lecture, MDPs and issues and all of that, some examples. And I'm going to go through an example in detail just to show how all of our approximation tricks actually play out. And then there's like 3 algorithms to solve optimal control problems. There's a linear programming approach, there's value iteration, and there's policy iteration. That's it. That's MDP theory. So we can knock that out in a few hours. And then there's the issue of hidden information. How far I want to go with that, I don't know. I mean, I think I should tell you about nonlinear filtering, how you create a belief state, and maybe mention something about the linear case and bandits. But that's like an equal amount of time, So let's say 3 hours, 4 hours on the algorithms and all that, 3 or 4 algorithms on partial information, and then we get to do RL and stuff for the remainder. Sound like a plan? And if some of you say I'm dying to hear more about bandits, I'll try. Yeah, it's a really cool, there's some beautiful ideas there, but it's a whole course in itself. All right, until Thursday.